This is going to be an advanced video where I talk about the models, the embedding models that you use within a retrieval system, a RAG system, retrieval-augmented generation. There's a new family of models out called ModernBERT that is faster and performs better than the older family that was out. So I'm going to go through that. I'm going to go through contextual document embeddings. This is another approach for training embeddings models, and it actually generalizes better than the embeddings you're probably used to using. And I found it performs very well. Actually, I'll show you an example of how well it performs on a data set about touch rugby. I'll briefly talk about Matryoshka embeddings. This is a way of sorting the dimensions of embeddings so that you can just use a subset of the full dimensions. This allows you to save space when you're storing your embeddings within a data set. So this will be a bit more advanced. If you want the basics on how to build a retrieval-augmented generation pipeline, you can take a look at my earlier video called Clean Up That Dirty Rag. But for now, I'm going to focus on keeping you up to speed with the latest models out there, how to use them and how they compare in terms of performance. I'll also show you how to fine-tune the ModernBERT family of models. So let's start off to talk about ModernBERT, what it is as a family, what the improvements are. I'll talk about the models built fine-tuned upon ModernBERT. Then I'll mention Matryoshka embeddings. This is where you save space on storing the embeddings. And then I'll talk about these contextual document embeddings, which is a different approach for training embeddings. And it's actually a two-stage embedding process. So it's a bit more complicated to implement, but it generalizes It generalizes better. So ModernBERT has been released by Answer AI. And what it is an update essentially on the previous families of model like SentenceBERT, like BERT, Roberta, DBERTA, these types of models. Now, what are they? You can think of them as pretty general kind of classifiers. They essentially convert strings of text, like a sentence, into an embedding with some dimension, say 512 dimension embedding. So it's a way to, with a pretty small model, convert strings of text into a vector, a meaning, an arrow that represents their meaning in high dimensional space. Now, there are a few improvements that ModernBERT brings. It performs better than the previous series of models, as you can see here in this table. Sorry, just moved from it. There we go. So performance a little bit better than the previous classes. But it's not just better in terms of the quality of the vectors that are generated, it's also faster. So if you look at it on this nice chart here, you can see the runtime in terms of milliseconds taken per token of input. And you can see the glue score, which is a measure of the quality of the embeddings. And these ModernBERT models are up to the top left, which means that they're faster, but they're also high quality. Now, why is that? It's because of a few tricks that are being used, and I'll talk about two of them. The first trick is that this is a transformer model, by the way, so it interleaves layers of attention with MLP, and it does that multiple times. So there's a layer of attention and multi-layer perceptrons, and that's repeated in multiple layers. But actually the full attention is only used periodically. So rather than doing attention throughout all of the layers, it's only done in some layers. And this saves you compute and it gives you speed up. And if you watched my video recently on reasoning models, you'll note that Minimax, which is a state-of-the-art model that has come out, actually it's not a reasoning model, but I talked about it in that video. That model also uses a reduced form of attention in many layers. In fact, it only uses full attention in 1 every 8 layers. And I believe, based on rumor, that a lot of the Gemini models in inference, they also don't use full attention in all of the layers. So this is one of the reasons for the speed up. And furthermore, the way that sequences, when multiple sequences are being fed in, they're fed in what's called an unpacked way, unpadded manner. So rather than feeding in sequences and just putting in these blunt pad tokens to fill out the rest of the input, instead of that, different sequences are combined together in order to avoid effectively wasting compute on pad tokens. So you can see here, instead of having this added padding space when you have a batch, they pack them all into one long sequence. So again, this makes the model more compute efficient. Now, ModernBERT itself is a base model. It's flexible in what you can use it for, but it requires fine-tuning if you're going to use it, at least to get the best performance. For example, if you want to use ModernBERT for a classification task, you could train it on some data that's split into different classes, and then you've got a classifier. But one of the main uses for this type of model is as an embedding model. So if you fine-tune it on passages of text and then a link to, say, questions or answers related to that passage, now you have an embedding model. And this is what Nomic have done. So Nomic, a different company to Answer AI, they've taken the ModernBERT base model, which is this flexible base you could use for many purposes, and then they have fine-tuned it to make Nomic ModernBERT embed base. And this model here you can use in order to calculate embeddings that are being used in retrieval. And you can see some of the different performance scores here. It's performing better on many of the metrics compared to Nomic's previous strongest model, which is Nomic Embed Text v1.5. So I'm going to take you through a look of using this model, and we'll see how it performs in some retrieval tests. Now, these models, the Nomic models that are trained on, that are fine-tuned from ModernBERT, they allow for what's called Matryoshka embeddings. And Matryoshka, I believe, refers to Russian doll, like many layers. And when it is talking about embeddings, it means that the embeddings are sorted. So if you have 512 embeddings, they're sorted according to importance. So the ones that are most important are at the start, and then as you work your way down, the dimensions become decreasingly important for describing the meaning of that sequence. And what this allows you to do is to flexibly just truncate the end of the embeddings if you want to save some storage space for your embeddings. So when you hear Matryoshka embeddings, and we'll try it out later, you can basically select a subset and just run with, say, the first half of the embedding dimensions or the first quarter or whatever you want. And you can do that. I'll just show you briefly the example here. I'll show it again later. You can do it by specifying the truncation dimension. And this means it's just going to keep 256 of the most important dimensions instead of the 768. So roughly a 3x reduction in terms of the size of the embedding vectors you have to store. Now, this won't reduce the memory that you need to run the model, because that's associated with the model weights and the sequence length you're inputting, but it does affect the memory you need, like the hard disk memory that you need for running or for saving your database of embeddings. If you wanted to reduce the embeddings, the size of memory, like the VRAM, if you're using a GPU, then you need to look at either using a smaller model, like using base instead of large, or you need to look at using some form of quantization. But yeah, it can be difficult to use quantization with these embedding models if you're using a GPU, just because the quantized forms are not really supported for fast inference. On GPUs, you can get some speed up by using the quantized versions of the models. If you want to look into that, I recommend going over to sentence transformers. Just search for sentence transformers and then quantization. And let's just quickly see. I think there's a comparison here. Let me see if there's a graph. Binary quantization. Yeah, I think I saw a graph earlier on. There are 8-bit formats for quantizing that will reduce the memory by a factor of 4 compared to 32 bits. Yeah, actually, this is where there are some benchmarks. And basically, if you're running on CPU, there are ways in order to get speed ups by using int8 formats without much drop in quality. But if you're on GPU, just because GPUs are very optimized typically for running in 32 bits or 16 bits, you don't really get that much speed up by going down to lower precisions. So yeah, unfortunately, using quantization, it can be good to reduce your memory if that's what's important, but it may result in some slowdown if you're using GPUs. If you're using a CPU, there is some opportunity, and I'll put a link to this below in the description of the YouTube. But let's get back on track. So I've talked about using Matryoshka style embeddings if you want to reduce the database size that you need to store vectors. And that kind of rounds out what I want to say about ModernBERT and the fine-tunes like Nomic ModernBERT. And I will show full examples in code of using those retrieval models. But before that, I want to talk about one more of the latest approaches to embeddings, and this is called contextual document embeddings. And you can find a paper by John Morris and Alexander Rush. It's from Cornell, talking about this approach. Now, the idea of contextual embeddings is that rather than just embed a piece of text on its own, when you do the embedding, you also embed some data from your background documents. And this allows the model to, in some ways, kind of search for your query among those documents through the transformer's neural net. Now, I'm going to take a step back from this. I know this might seem circuitous, but to understand why contextual embeddings work well, it's worth understanding why BM25 or Best Match 25 works well. So let me explain briefly BM25. I've explained it before in the video on Clean Up That Dirty Rag, but let me briefly explain it, why BM25 is very useful, and I highly recommend using BM25 in addition to using embedding models. And if you understand why it generalizes well, that will help you understand contextual embeddings. So BM25 is a form of keyword search, but instead of just searching for keywords within your documents, you also weight the importance of the documents according to the frequency of the terms. So if there's a term that appears very rarely across documents, but it's in your query, you're going to more heavily weight the documents that do have that rare term because it's in your query and it's rare. If you've a term that's very common, like the word the, then you're going to de-weight it. And you can see that's useful because very rarely is the word the going to be helpful in picking which document to choose. Whereas some obscure word like daffodil or something, if that's in your documents and it's rare and it's in your query, you probably care a lot about those documents. Now, BM25, as I said, it's a keyword search method, so it doesn't work well from a broad meaning standpoint. Like if I say happy and in my query, I've got the word happy, but in the documents, there's the word content. That's obviously not going to match because it's an exact match type approach, whereas that's a meaning-based match. And matching based on meaning is where neural networks and transformers excel. So this is not where Best Match 25 works well. However, Best Match 25 generalizes extremely well. Now, what do I mean by that? I mean the algorithm for doing that frequency search. It's not in any way specific to the data set you're working with. It's a general approach based on frequencies and then based on keyword match. So even if I have a document set that has a totally new word that has never been seen before, Best Match 25 is going to work if I have it in the query and if I have it in the document set. And that's what I mean by Best Match 25 generalizing well. And unfortunately, transformers and neural networks, they do not generalize very well, because if they have a word that has never appeared in the corpus for training, there's just no real way for it to generalize to understand what that word is. It's just going to receive some random vector that won't be oriented with anything else that's particularly close. So Best Match 25, while it doesn't do well on meaning-based comparison, it generalizes extremely well. And so when you have a new set of documents without having to do any kind of fine-tuning or training, if you have a new word and there's an exact match, it's going to have a chance of finding it, whereas using an embedding model has got no chance of finding it. Okay, so we understand Best Match 25 works well because of its ability to generalize. And actually, this is why contextual document embeddings work. So, well, why they work and have advantages over just a standard embedding model. In a standard embedding model, you've got a corpus of data, you fine-tune your embedding model on that, and then you use that model in order to generate a vector. But that vector you generate depends only on the query you pass in to the contextual embeddings model. It does not depend on your set of documents that you're going to retrieve from. So if you've got documents that were never within the original corpus, it's not going to depend upon those in any way. It's not going to have any way to get that info. But in a contextual document embeddings approach, when you train the model, every snippet you pass in and train it to become a vector, you additionally pass in a batch of related documents. And this means at inference time, you're going to be able to do the same. And you can pass in not just your query to embed, but also the background documents that you're going to retrieve from. And yeah, you'll just have to stop and think about this a few times, but it is very analogous to Best Match 25 because the documents are being input to the model as well as the query. And this gives the model a better chance of being able to develop those kind of inverse frequency relationships and tell which parts of the documents are going to be most important or not. So this has to be done in 2 steps. Don't worry if you don't get it the first time. This is what I just described during the training. You not just pass in each of your samples. For every sample you pass in, you also pass in a batch of related documents. And the way the flow works is the batch of related documents gets turned into an embedding. Actually, there's, I think, 512 related documents that are passed in. That is kind of pooled into an embedding representation. That is passed into the second stage, which you can think of as a classic embedding model. It takes in the pooled representation of related documents, plus it takes in the query that you're actually interested in. And so when you go to inference time, and you'll see this in practice when I work on the touch rugby rules, we're going to embed the background documents. Then we'll just store this. We don't have to keep repeating this. We take the embeddings of the background document and feed these in addition to the questions we have about touch rugby in order to get an embedding representation of that query. And yeah, this basically gets some of the benefits of BM25, but it also gets all of the benefits of the embeddings approach. And it turns out, to get a little bit technical, it seems a little bit more stable in some ways for training. Often training embedding models, you need to put in what's called hard negatives. A hard negative is when you have 2 phrases. One of the phrases looks like it's related to the first phrase, but it's actually not related. And this can happen if you ask a question like, maybe something like, what is the capital of France? And then another question is, what is the capital of Germany? And yeah, I guess maybe those are somewhat related because they're both asking about the capital of a city. But on the other hand, by looking at one question, you're clearly not going to get the capital of Germany from looking at the question for what is the capital of France. So maybe in some ways, you've got this kind of hard negative. It appears that the 2 questions are quite similar, at least if you look at the percentage of words that are similar, but actually they're not that similar. Okay, so this is the contextual embeddings approach, and we're going to see how this performs in practice on the touch rugby rules dataset. It's implemented here as the CDE small v2 model. And yeah, there's the note here on the parameter count because you've got 2 models. You've got one that's used in order to embed your background documents, and then you've one that's used at inference. But really, the one that's going to be loaded into memory for inference is going to be this one. So it's maybe not quite as big as you think when you just look at the raw number of parameters or the size in gigabytes of the weights. Now I'm going to put all of this into action and show you the performance of different approaches. The scripts I'll be running are available in the advanced fine-tuning repo. You can check out trelis.com/advanced fine-tuning. And this repo now has a lot of content on data preparation for fine-tuning, different methods. It also has the scripts around retrieval in general, and you'll find the ones today in the branch called retrieval-v2. So that's for those of you who already have access here. So I've cloned that repo and I'm in the branch for V2. And let me give you a sneak preview, actually a full preview of the results I get. So here's what I'm going to run through. First, by the way, I've got 11 questions I've set up asking about the rules of touch rugby. And if you're familiar with my channel, you'll know I pretty much often cover that because touch rugby is kind of an obscure sport that language models don't really understand that well. And I often like to run a retrieval system on these international playing rules here. So I'll retrieve some chunks and try to answer questions. In fact, you can check the questions here. These are the 11 questions. Just as a sample, how much is a try worth? And the answer is 1 point. And actually compared to the V1 of retrieval, I have now put in a judge to help me automate the evaluation of the questions and answers. So I did that, and I did it for a wide range of retrieval approaches, and I got these results. So let's look at those. I'll increase the size here of the screen. So the basic approach I took was BM25, no embeddings, only allowing for 3 chunks of retrieval. And I got 6 out of 11, so 54%. Then using an older embedding model, which I think now is outperformed by ModernBERT, I got 63%. Then using ModernBERT, this is the Nomic model, by the way, the base model, I got 72. And when I used Matryoshka embeddings, so I only used the first 256 dimensions, I got a slight bit worse, but not too much worse. Then I fine-tuned the ModernBERT model and I improved the performance a little bit. And then I took a look at the CDE type approach, the contextual document embeddings, and I also got 81%. That's without any fine-tuning. And actually, when I combined CDE, so 3 chunks of CDE with 3 chunks from BM25, I was able to get up to 90%. Now, the one question that none of these models get is kind of interesting. I think if I increase the number of chunks, it would get it. And by the way, 3 is too small a number of chunks. I recommend usually doing a minimum of 6, usually 6 embeddings and 6 BM25. The reason I do 3 is because I want to make it a hard test in order to measure the retrieval accuracy. So yeah, just to recap, BM25 55, use an embeddings model, performs a little bit better than BM25. Sometimes this order can be flipped. Then if I use a stronger model, it performs better, like the more modern one. Then if I fine tune it, it performs better. The CDE seems to perform well even without fine tuning. That's an example of how it does well in terms of generalization. And if I add CDE with BM25, that's when I get the best performance and I get nearly all of the questions right there. So let's take a look through running all of these requests here. And to do so, I'm going to set up a virtual environment, uvvenv, and I'll install the requirements. So you want to, let me just start, I'll throw out that terminal, start a new one. So you'll run uvvenv. I've already run it, so I don't need to. Then uv pip install requirements. In the env file, you need to provide an endpoint that's going to do the judging and also that's going to answer the questions. So you can take a look at sample.env. I've updated the script so any model is supported that has an OpenAI style endpoint, which includes Gemini now. And you can see in this sample.env, I'm going to specify a few things. I'm going to specify if I'm using a runpod endpoint, I'm going to specify the endpoint itself and the model. I'm going to specify my choice of embedding model. Of course, this will be updated to the ModernBERT one. And then if instead of using a runpod endpoint, I want to use Google or OpenAI, I can specify the API endpoint. This is the API endpoint now for Gemini if you want an OpenAI style endpoint, and then specify the model. And actually, I'm going to use Gemini 1.5 Flash for this. There is a newer version of Flash, but it's experimental and you hit the rate limits. So I'm going to use this one here for now. So I've installed that, set up my virtual environment. And the next thing I need to do is create embeddings for my document. So basically I need to split the document into chunks. I actually use a method that will cleanly extract sentences instead of breaking sentences in the middle. The chunks will always have a whole number of full sentences. Again, you can check out my earlier video on retrieval for that. So I've run this script here, uv run and create train queues and embeds. And this just creates the embeddings for my chunks. So it creates my chunks, creates my embeddings. And optionally, it's possible to create some questions as well that can be used for fine tuning. And I'll talk about that a little bit later. But for now, yeah, let's just run this here. And I'm going to run it by setting my embedding model to the Nomic model, because that's the model that I want to test out first. So here, I'll do this in my .env file. Let me pause the video and I'll set that up now. Okay, so here I've added in a few new options, the ModernBERT model, the base model, then a fine-tuned version I'll run later, and then the CDE model. So I'm going to start off with just the embedding model, and I'm going to run this script here to create the training questions and the embeddings. And all this is doing is splitting up the text into chunks and then calculating the embeddings by downloading the model. And you have the option here to run one or all of the chunks. I'm going to run all of the chunks. There are 61 chunks that this document has been broken into. You can see that's running in just 2 batches. So you can pretty much fit, and I'm running locally on my Mac for the embeddings here. So you can see it's fitting about 32, a batch size of about 30 within each. All right, so the data is now written. I can go up and take a quick look at the data. It's in Parquet format, which could be pushed to Hugging Face, but it's also available in JSON format. And yeah, the format is there's a chunk here, and then there's the embedding for the chunk. Okay, so now that we have embeddings, we're able to start running retrieval. And the way to run retrieval is to calculate the embedding for the query, do a cosine similarity with the database of embeddings for all of the chunks, and find the closest chunks for that. During the script, there's the option to run with Matryoshka truncation and select how many of the dimensions we want to actually use. So I'm going to run now, and I can do that by running this uv run test.py. And optionally, I can pass in print prompt. If I just want to print out the full prompt, it'll save the prompt so that we can inspect it later. So I'll run this, and I'll just run it for one row of the data, one question instead of the full 11. But it's going to take me through the steps. Do I want to use BM25? I'm going to say no. Do I want to use similarity? Yes. I'm going to use cosine similarity. This is generally how models are trained. I'm going to use 3 chunks for retrieval. I'd recommend more normally, but I want to make this hard, so I'm just picking 3. And there's also the ability to use a re-ranker. Generally, I'm not a fan of re-rankers. I think it's an extra step that adds complexity. And I also think if your embeddings model is bad, a re-ranker is not going to help because you're already missing chunks, so they won't be possibly re-ranked. Additionally, a re-ranker can miss chunks that your embedding model correctly picked out. So generally, I'm not a huge fan of re-rankers. If you are, let me know where you think it works well, but I think it adds complexity. So I'm going to select none. And I'll just run it on one row here. So I'm generating, first of all, the embedding for the query. It happens very fast. Then that's cosine compared to the embeddings database. And then it picks out the chunks. And you can see here, it's picking out 3 chunks. The question that's been asked is, what are the dead ball lines? What's the purpose of the dead ball line? And yeah, it's getting the right chunk. And the judge is coming back. I'm judging this response here by comparing the assistant's response to the ground truth, which is in my original JSON. And it's scoring 1 on this question. So it's working well. Now, it's also printing out the results, but that's because I've run this test before. And yeah, when I run with this base model, in fact, it looks like I've selected the wrong model here. So I'm going to rerun that. So I've just unset the embedding model. I'll rerun this script again. No, yes, cosine. No truncation, but you could do truncation there if you wanted. And indeed, that's what I did. And I got a small reduction in performance, just 3 chunks per retrieval method. And then I'll run just one of the rows. Yeah, so here, what I didn't do was unset my environment variable, so it was grabbing an older environment variable. But now it's written the result for this question, and I've got the results for all the questions, and it scores 8 out of 11 or 72% for using this base untrained model. So this is how you can run an embeddings model. And indeed, I ran the same with the older model and then the newer model to generate that plot of results that I showed you already. Now, I want to show you 2 more things. One is how to run the CDE model, and then I'll show you how to fine-tune the ModernBERT model. So for running CDE, things are a little bit more complicated. First of all, you need to comment in the CDE model here. So I'm actually in my environment variables here. I don't think I'm exposing anything. And I've commented in this embedding model here. So I'm now going to move to using CDE. And I will show you the script. By the way, all the scripts I've gone through in detail in the earlier retrieval video. That's why I'm not repeating myself here. But I will show you the scripts now for this CDE model because the flow is a little bit different. And to do that, I need to look at test.py, and I need to look at the CDE scripts here. And basically, if the CDE model is being used, so I'm going to search for CDE, we have to do things a little bit differently. So we need to not just calculate an embedding for the query, we also need to load a set of embeddings for a reference data set. And the reference data set is going to be all of the chunks that I'm using, that I've generated from my document. And you can see here that I'm loading some saved embeddings. So actually, before I run inference using the CDE approach, I first have to create embeddings for my full document set. Now, actually, the CDE model doesn't take in embeddings from all of your documents. It only takes in, ideally, a random representative selection. And it actually takes in 512. Now, I don't have 512 chunks. If you recall earlier in the video, I only had 61. So what I've done is just replicated those a few times. Maybe there's a better approach, but this actually works fairly well. And I've just multiplied those to get up to the required number of 512. If you have a larger data set, you're going to have more than 512 strings. So you would just randomly select 512 out of those. And in fact, this means that when I'm initially creating the embeddings for my documents for each chunk, I also need to create the embeddings for my reference documents. Really what I need to do is I need to pass the reference documents, 512 of the chunks, through the first stage model in order to get the embeddings that are going to be stored and reused and passed into the second stage at every stage we run inference. So again, I had to modify my script for creating embeddings so that it doesn't just create embeddings for chunks. It also saves that data set. So you can check that here. If CDE is within the embedding model name, then we need to get the required sample size for the data set, which I said was 512. So we'll establish we need 512 and print that out. And then we need to take a random sample of chunks if we have more than required, or if we don't have enough chunks, we need to kind of duplicate the chunks that we have until we get to the required 512. And then we need to save those into the database. So here I'm getting the embeddings, getting the dataset embeddings, which specifically means I'm using stage 1 of the model. And once I have those embeddings, then I'm able to start saving these items into the database. And that's what's happening down here in the code. So let's run this script here to now create the training questions and embeddings. Again, I'm not creating training questions here. I need to pass in the flag create questions if I want to do that. I just want to create embeddings for each chunk using the CDE model. But I also want to create the data set of reference embeddings. So I'll run that here. And you can see we're using this CDE embedding model. I'm going to run it on all of the chunks. And you can see here, it's generating a dataset embeddings for the CDE model. And once it's done that, it will move to calculating the embeddings for each of the chunks. So first the dataset embeddings, the reference dataset, then the chunks. See, so here, now it's going to start to calculate the embeddings for the chunks. So first the dataset embeddings, next the embeddings for the chunks. Okay, so now we've saved the embeddings and the dataset embeddings for the CDE model. And if you check the JSON where they're saved, and by the way, you would typically save them to a Postgres database, but I'm saving them to JSON here just to make it easy to spot. And when I search for the word dataset, you can see that I'm not just storing the embeddings for each chunk, I'm also storing the dataset embeddings right here. And yeah, this allows me to save them so I can use them and pass them in at inference time when I'm running the second stage. So now we can run the second stage, and I'll do that by saying run test. And you'll see it's going to detect I'm using the CDE model. I'll say no to BM25, yes to similarity cosine here. I'm going to use 3 chunks. I'm not going to use a re-ranker, and I'm going to run just on 1 row. So we'll just answer 1 question. It's loading the model, and it's using CDE. And yeah, what it's doing is passing in 2 things. It's passing in the embedded query. It's passing in the query, but it's also passing in that reference data set of embeddings in order to get the final. And yeah, as I showed earlier in the graph, when you run for all the questions, it gets 9 out of 11. So this is performing really well, especially for a model that's not been fine-tuned on the data set. Okay, so that was contextual document embeddings. It is a 2-stage process, so it's a bit more work if you want to code it up, but it does generalize really well, and I'm impressed with the performance of it. So the last thing I want to do is talk about fine-tuning embeddings, and I'm going to fine-tune the Nomic BERT model. And as you saw in the table, in the graph, I did improve performance a bit when I did the fine-tuning. Now, I described this in much more detail in my original retrieval video. There are a few ways that you can fine-tune models. Two ways are to generate either pairs or to generate triplets. I'm going to generate pairs here. And what you need is chunks that have a question that is closely related to that chunk. So it's a question that probably would be answered by needing the content in that chunk. And you can do this through a reverse process using LLMs. Basically, you cycle through all the chunks in your data set and you ask the LLM to generate some questions. So I can actually show maybe a quick snippet. If I have create train queues and embeds, it's the same script that creates the embeddings, but optionally you can pass a flag to create questions. And I can maybe find the LLM call. And yeah, here's the LLM call. Generate exactly 5 questions based on the following text. Your response must be a valid JSON array of strings. And the instructions are generate exactly 5 questions that can be answered. Each question must end with a question mark, format it this way. Do not include any text or explanation, and then an example of the required format. And when this script here is run, it's going to give a data set that looks just like this. In fact, I'll have to run it again because I've already run without passing the create questions prompt. So here I'm going to pass UV run create train queues and embeds, and I'll pass the flag for generating questions. So here I'm creating embeddings for my data set, but also creating questions I can use for fine tuning. I'll just do it for one chunk. And when they're created, I'll be able to check my data and I should be able to see questions. It's not actually finished just yet. Here it's calculating the data set embeddings because we're using the CDE model. Now it's getting the embeddings for one chunk because I've only requested one chunk. And I'm going to say yes, generate new questions. Optionally, you can pass in a subject. This kind of grounds the question in the topic. So I'm going to say touch rugby rules. And now it's calling the LLM. And yeah, creating a question. So if I check here now, yeah, if I search for question, you can see the 5 questions that are being created for this initial chunk. And the initial chunk talks about when the review of the rules was conducted. So you can see here there are 5 questions. And the way the training works is now that we know questions that are associated with each chunk, we can set up a loss function where we basically try and get the model to point the vector for a question in a similar direction to the chunk and to point it away from other chunks. So actually the training will randomly pick other chunks from the data set. This is using MNRL, and it's going to encourage the vectors for the questions that are related to this chunk to be moved towards the chunk. And it's going to encourage the vectors for other random chunks to be pointed away. Now, there is a risk that some of the other chunks are actually relevant and should be pointing towards it. It's probably not that big a risk if there's not too much overlap in the content of your chunks. But that's something to keep in mind. The approach with triplets is a little bit different. You can set up positive, negative pairs. Basically, you have a question and then you have a chunk that is related and a chunk that's not related. The question might often be called an anchor. And you can use an LLM, for example, to rate chunks as being relevant or not. So if you get a given question, you pass it to an LLM along with many, many chunks, you can rate the relevance of each chunk. And if you have the relevance of each chunk, say on a 5-point scale, you can create triplets by taking one of the 5s for this question and one of the 1s. And that gives you a positive, negative anchor triplet. And you can train the model now to basically move the vector such that the vector of the question is moved towards the 5, the relevant chunk, and away from the vector for the chunk that is rated as a 1. So that's a very quick overview of something I described earlier in the earlier retrieval video. I'm going to use pairs here. It's a little bit more straightforward, but you can use either. And you can do so just by running the script for either creating pairs or creating triplets. If you're going to create triplets, it will additionally need to call the language model to assign ratings of relevance to the chunks. So that script for running triplets, let me see where it is. Yeah, the triplet script here takes longer to run. It can take quite a while because it's got to rate the relevance of the scripts, whereas this one here is going to be pretty quick. So I'll just do uv run, create q chunk pairs.py. And yeah, you can optionally push that to hub. So actually, I have pushed such a data set to hub. Let's see if we can find it here. Yeah, so here we go, touch rugby ModernBERT pairs. And you can see every chunk, it's repeated 5 times because it's got 5 questions related. And given this data set, we're going to be able to grab these pairs in the training script and use it for training our embeddings model. So let's move to do that. To do the training, I'm going to open up an IPYNB notebook. These are available here in the fine-tuning scripts folder. There's one for fine-tuning cross-encoders, but as I said before, I'm not a fan of cross-encoders or re-rankers. So I'm going to use the sentence transformers script. This is for fine-tuning embeddings models. And I'll walk you through how the script works. I'm going to run it on Mac. It takes me about 10 minutes to train an embeddings model, which is not too bad. It would run faster if I run it on GPU, and I did that in the last video. It's definitely way faster. But actually, I had trouble running on GPU when I was fine-tuning the Nomic BERT model. Probably there's a way to make it work well, but I would need to dig more into it. So I just stuck with running here using the notebook on my Mac. And you could run it on CPU either. I think it would run in a reasonable amount of time as well, because these models are not very big. So the first things to do are to do some installations. So I like setting up a virtual environment. Usually I'll have set up a virtual environment in the folder, so I'll cd into fine-tuning scripts. And then I'll do uvvn to create a virtual environment. And actually I can run within VS Code or Cursor, I can run this IPYNB notebook just by clicking up here, selecting Python, and then running the Python environment. Just one thing that has to be done before then would be uv pip install IPY kernel. So you need to install IPY kernel so the kernel is able to use the virtual environment. If you're running on Collab or in RunPod on a remote server, then actually I think using a virtual environment can be more hassle than it's worth. You're better off just to run the installations directly, maybe not even using UV, just use pip install and install them directly into the server environment. So run these installations here. If you're running locally, you need to run IPY widgets. Usually that's pre-installed if you're using, say, a Jupyter Notebook on RunPod. Next, I like to import this environment variable for HF transfer. It gives me fast weight downloads from Hugging Face. And then I like to log in to Hugging Face so that I'm able to push my models up to hub. Next, I'm going to load the embedding model. And most of my fine-tuning videos, I'll use transformers, but here for embeddings models, I like using sentence transformers. It's kind of a standard. I'll load the model to CUDA if CUDA is available, otherwise MPS, or set it to CPU if you're not using a Mac. Now, we're not going to use mixed precision. I think there's some release of Torch that will soon support mixed precision on Mac, but for now it's best to disable it if you're on CPU or using Mac. And then this line here just loads the model onto the device. And the model I've specified, where have I specified it? Right here. It's the Nomic AI ModernBERT embed base. So with that done, I'm not going to apply LoRa. This could be done if you want to fine tune through transformers, but these are small models, so we'll just fine tune all of the weights. And we'll do that on the data set I just showed on Hugging Face, the ModernBERT pairs. And so we're going to load that data set, split it into training and tests. So 10% will be reserved for the eval data set. And once that's loaded, we're going to start to run the training, but first we need to define a loss. And there are a few losses you have that depend on the training format you have. If you're training with pairs, you can use multiple negatives ranking loss. This is MN or L, which is what I mentioned earlier. Basically, it will take the pairs of chunks and relevant questions, and it will randomly select other chunks to kind of assign as negative. For triplets, you can use a triplet loss, which basically tries to move the anchor towards the positive and away from the negative. There's also a cosine loss, a variant of cosine loss. You could consider that as well for pairs. So next, we're going to set up a few parameters here for weights and biases. You can just uncomment the weights and biases ones if you don't want to connect. And then we're going to set up the training arguments. I'm using a large batch size. Probably could reduce this, especially if you run out of memory. There's no problem reducing that. And my learning rate is quite small, 5e minus 6. I actually used a higher learning rate on ModernBERT and it wasn't stable. Although this may be a little bit too small. So I think the optimal value is probably between 5e minus 6 or maybe 1e minus 5. I've set FP16 training to false. So we're, I think, going to be training in 32 bits. And I'm going to run for 1 epoch. With that, I pass in the training and eval data, the loss that we defined, the arguments above and the model, and then start that training. So you can see here, I ran the training. It took, actually took me 40 minutes last night. So sorry, I said 10 minutes. 40 minutes is quite a bit longer. And yeah, you can see it looks stable. The training loss is maybe not changing too much, but the validation loss is definitely falling. It's falling still by the end of the run, which means probably I should have used a bit of a higher training rate. And yeah, it's even possible if I train it further. I moved from getting 7 out of 10 right to 8 out of 10 right by using this approach. Was it that, or was it from 8 to 9? Either way, I got an improvement of about 10% by fine tuning, but probably if I use a higher learning rate, I might be able to, I won't say probably, but possibly I would be able to get an even higher performance. So then I save the model and I push the model up to hub, and you can check out the model. I think it's ungated, ModernBERT embed based touch rugby, fine-tuned V2. And given this, I can now run inference. So if I go back to my environment variables, I can now choose that fine-tuned model, and I can run, I need to get back to my root, uv run test.py, and I'll print the prompts. And let's run that. No BM25, yes, similarity, cosine, 3 chunks, and no re-ranking. And I'm going to just run 1. So it's going to use my fine-tuned embedding model. And yeah, it scores 1, so it gets this answer correct. And yeah, when you combine it with all the others, it moves me to getting 9 out of 11 instead of 8 out of 11. But as I said, if I optimize the learning rate and test it out using a higher learning rate, I think there's a chance I'd be able to get this model to perform a bit better. Now, could you fine-tune a CDE model? This is not CDE. Yes, there's no reason why you couldn't. You would have to set up the data pipeline, that's the data collator that's going into the trainer, so that it takes a relevant batch of data as well as each query. Because remember, you need to have the reference data set and the query for the second stage of the model. And if you were fine-tuning, I think you would just be fine-tuning the second stage. I mean, you probably could go to town if you had a massive data set and decide you want to fine-tune the first stage as well. But the most straightforward, I think, would be to just fine-tune the second stage if you're doing CDE. But it would require you to work a bit with Cursor or ChatGPT to get the data collator into the right format. Furthermore, if you're going to fine-tune, you're kind of bringing yourself already into the context of your document set that you're using fine-tuning for. So maybe the benefits in that case of using CDE are relatively smaller than they would be if you're just using untrained models, unfine-tuned models in the first place. And that brings us to the end of this more advanced embeddings approach. To summarize, I'll give you my boring tips and my advanced tips. My boring tip is use BM25. I think I see a lot of tutorials that just use embeddings, and I think that's a mistake because BM25 is somewhat orthogonal to traditional embeddings approaches, and it generalizes very well. So if you have any new data at all, it's going to give you a chance to grab it. Whereas with embeddings, you probably have no chance for some totally new queries. That's my boring tip. I've given that one before. My more advanced tip is probably it's time to move to the ModernBERT models, or the, say, fine-tunes off that like Nomic are offering. They just provide better performance with higher speed. And I would highly recommend trying out the CDE models and seeing if it performs well on your data set. It's pretty nice if you don't have to do fine-tuning, if you can have a model out of the box that's going to generalize well. And the fact that you pass in a reference data set gives the CDE model that kind of advantage. I'll put all of these links below in the description. And as usual, let me know if you've any questions. Cheers, folks.